Hey everyone, welcome to Neural Notes, show where AI comes alive. Smash that subscribe button and ride the innovation wave.
So when I say the words computer science, what's the first thing that pops into your head? For a lot of us, it's probably a dark room, a glowing screen, and just endless lines of code. But what if I told you that's just one tiny piece of a much, much bigger and way more fascinating picture? Let's pull back that curtain and really demystify what computer science is all about. Okay, let's get the big one out of the way right now. Is computer science really just a fancy way of saying computer programming? It's a super common idea, and I get why. Programming is often the first and sometimes the only part of computer science that people ever see. But the field, it's so much broader than that.
I love this quote. It's a little provocative, right? It kind of playfully messes with our assumptions. So if computer science isn't a science in the traditional sense, and it's not just about programming, then what in the world is it? This really sets the stage for us to dig in and find out.
The truth is, computer science is this huge, sprawling discipline. We're talking about everything from the deep theory of what's even possible for a computer to do to the massive scale engineering of software systems. For instance, some computer scientists are asking these huge questions like, are there problems that a computer can just never solve? Others are focused on making things not just work, but work unbelievably fast. It all proves that the real core of computer science is problem solving. Programming is just the tool you use to write down your solution.
And that brings us to something I'm sure a lot of you have felt. Learning to program can feel incredibly hard. So why is that? Well, it turns out there's this fantastic analogy that really gets to the heart of the struggle. We'll call it the poet's dilemma. Imagine this. Someone asks you to write beautiful, moving poetry in French. The catch? You don't speak a word of French, and you've never studied poetry a day in your life. See, you're trying to solve two completely different problems at the exact same time. First, you have to learn the language itself, the grammar, the words, the syntax. Second, you have to learn the art of poetry. Learning to code is exactly the same. You're learning a language, like Python, and you're learning the art of problem solving, all at once. It's a serious double whammy. So you give it a shot, right? Your first attempt at translating that French poem might look a little something like this. It's a literal word-for-word job. The words are there, they're technically correct, but it's just clumsy and awkward. It completely misses the beauty and the soul of the original. This is a perfect picture of a beginner's first program. Sure, it might run, but it has no elegance, no clarity. But then you practice. You don't just learn the words, you learn the art. And you come up with something more like this. It captures the rhythm, the rhyme, the feeling of the original poem. And that is the goal of a good programmer. Not just to write code that a computer can understand, but to craft a solution that is clear, efficient, and maybe even a little bit elegant. So how do you get there? How do you go from that clumsy first draft to the elegant final poem? Well, it takes a fundamental shift in how we even think about what programming is. It's not just about barking orders at a machine. It's about something way more profound. This brings us to the first absolutely fundamental rule of good programming. It is so simple, yet it's the one step that basically everyone is tempted to skip.
That's it. Think before you program. The single most common mistake is getting a problem and immediately jumping in and just starting to type code. But the real work isn't the typing, it's the thinking. You have to really understand the problem first and then design a clear, logical plan for how you're going to solve it. You have to separate the problem solving from the programming. And now for the second rule. This one really reframes the whole point of what a program even is. Most beginners think the most important thing about a program is that it works, but that's not quite right.
This gets to the absolute heart of it. A program is for people first. It's an essay that you write to explain your solution to another human being. And you know who the human who's going to read it most often is? Future you. When you come back to that code 6 months from now, it has to make sense. It's an essay that just happens to be so precise and logical that a machine can run it.
Okay, but wait a second. That brings up a huge question, right? If a program is a human-readable essay, how on earth can a machine, a pile of metal and silicon, possibly understand it? To answer that, we have to peel back the layers and see what a computer really is deep down.
If you were to crack open a modern computer chip, you'd find a level of complexity that is just staggering. We are talking about billions, with a B, of microscopic little components, all packed into a space smaller than your thumbnail. It's a number that's almost impossible to even wrap your head around.
So you have to wonder, What are all those billions of parts actually doing? How does this ridiculously complex machine take our human-readable essays and turn them into something that actually happens? The answer, believe it or not, is surprisingly simple.
It all comes down to this simple chain. Every complex computer is built out of things called logic gates. And those logic gates, they're built from even simpler parts called transistors. And what's a transistor? At its heart, it's nothing more than a simple on-off switch.
That's the big secret. A transistor is just an electronic switch. The easiest way to think about it is like a faucet. A tiny little signal, like you turning the faucet handle, controls whether a much bigger flow of electricity can go through. It only has two states, on or off, true or false, 1 or 0. That's it.
And this timeline, this shows the absolute magic of modern computing, this exponential growth we call Moore's Law. We have gotten absurdly good at making these little switches smaller and smaller and packing more of them onto a chip. In 1971, a processor had a couple thousand of them. By 2008, it was over 2 billion. And every single one of them is just a simple on-off switch.
So, okay, how do we connect these two worlds? On one side, we have this beautiful abstract idea of a program as a human essay. On the other side, we have the nuts and bolts physical reality of billions of simple switches. What is the bridge that connects them?
Let's go back to some actual code. This little program to figure out a circle's circumference is a perfect example. Look at it. It's a series of clear, logical steps that represent a thought process. Get a number, turn it into an actual number the computer understands, apply a formula, and then show the answer.
Now here's the incredible part. When this program runs, that simple, abstract thought, your idea, gets translated into a sequence of electrical signals that flips millions and millions of those tiny switches on and off in this perfectly coordinated dance. It literally turns an idea in your head into a physical process that produces a real result.
And that leads us to the most powerful idea of all, I think. A program is your thought made manifest. It's a way to capture a problem-solving process so perfectly that not only can another person understand it, but a machine can actually execute it, bringing your thought to life.
This is the true promise of programming. It is one of the most powerful tools for creativity and problem-solving humans have ever invented. You can have an idea for how to solve a puzzle, or how to compose a piece of music, or how to make a robot dance. You write that idea down as a program, and the thing you imagined actually happens.
Programming gives you the power to make your thoughts executable. It turns your ideas into action. So really, the only question left is this: what will you think of next?